Okay.
And with that, yes, we'll move on to the first talk. So Frederic Chevy is professor at École Normale Supérieure in Paris. He studies the dynamics of quantum and classical fluids. His latest research involves the study of strongly interacting Bose gases and mixtures of bosonic and fermionic superfluids. And this morning, or today, he's going to tell us about the conductivity spectrum of ultracold atoms in optical lattices.
So thank you very much for this introduction. Today I want to tell you, so first I would like to thank the organizer for setting up this meeting and reviving our community that has been hurt by this pandemic situation. And actually I'm going to tell you about a pre-COVID collaboration on which I worked with Joseph Sawyson in Toronto. So they did the experiment and they kindly allowed me to participate to the discussion and to the analysis of their data. And my talk will be dealing with the problem of optical conductivity of ultracold atoms in optical lattices. Here, optical means AC, so time-dependent conductivity. So this is very much in line with what we heard yesterday in the talks, for instance, by Tilman Nesslinger about the conductivity of fermions, but in a slightly different context. So I don't have to repeat what he said, which is that obviously in atomtronics, when you want to transport particles from one place to the other, it's very important to know about the dissipation and decoherence during quantum transports. But in addition to that, looking at transport properties is also a very powerful tool to get access to the property of newly found materials. So when you're dealing in material science or condensed matter, one of the most direct way of getting information about a new compound is to simply connect leads to this compound and look at how the material conducts electricity. And so, for instance, that's how superconductivity was discovered, and especially high TC superconductivity. That's also how Kondo effect. So by looking at the temperature dependence of magnetic materials was detected, was observed, and obviously also quantum Hall effect, where you see plateaus in the conductivity as a function of magnetic field. And so the idea is to do the same with cold atoms, to be able to probe the properties of a strongly correlated material. And so the experimental platform in our case is the experiment of Joseph Sawyson group in Toronto, which is a quantum gas macroscope experiment where they trap potassium-40, which are fermions, in an optical lattice, and they have a high resolution microscope that allow them to observe the atoms individually. And so you see here a picture of these atoms where each dot here is an individual atom. And obviously they're not the only one doing these kind of experiments. You have now lots of other groups who can trap bosons or fermions in this kind of microscopes. So here I put a list, but it's probably not complete because there are new microscopes popping up almost every month these days. So one of the most interesting points of quantum gas macroscope experiments is that it allows us to really simulate one of the PET models from condensed matter theoretician, which is the Hubbard model. You know that in this model is described by essentially two parameters. Here you have the kinetic energy that describes the hopping of the atoms from one site to its neighbors, and it's characterized by T, which stands for tunneling. And in the Hubbard model, the interaction is only on site between fermions of opposite spins. Here we're talking about spin 1/2 fermions, and you will measure the interaction of two atoms which which happen to be to occupy the same site. And there is no other parameter in the let's say pristine Hubbard Hamiltonian. In many cold atom experiments, you need to add an harmonic trapping that confines the atom in a finite volume. So some experiments are performed in the in a box, but here this is the traditional harmonic trapping. So in Joseph's experiment, you have this additional parameter here, K, which is the stiffness of the harmonic trapping. And so the idea is to probe as I said, the conductivity. So you need to probe conductivity. You need to create some current and some oscillating current. So yes, so I should say that we can control all the parameters of the experiments. And so for that, you need to know that the harmonic trapping, which is here, is actually created by a pair of laser beam, 4D2 laser beam that create an attractive potential. And to probe the conductivity, what they simply did is to shift the position of this beam here and to oscillate, to wiggle the beam like this at a constant frequency, sinusoidal. And since they can measure the position of each atom individually, what happens is that they can reconstruct the position of the center of mass of the whole cloud. And what they see is this kind of oscillation. So there's a transient regime here, and they reach a steady state. So the frequency that they explore is between 10 and 10 to the 40 hertz, 10 kilohertz. And they then measure both the amplitude and the dephasing of the response of the atoms with respect to the exciting potential. So it's really as if they were applying a constant force, but which oscillate constant in the sense that it's homogeneous, but it's not constant in time because it oscillates at a given frequency. And so the idea is to measure the response of the system as a function of the frequency. So this idea of measuring the conductivity spectra was actually proposed by Wu, Taylor, and Zaremba in 2015. And so, as I said, what you measure here is the global current. So you just sum the velocity of all the particles. And in the linear regime, you have a proportionality relation between the applied force, so at a frequency omega, and the current, and you have a response here, which is a tensor, because you can look at a current in a direction which is not that of the applied force. So there are lots of properties, general properties associated with this response. In particular, the fact that the real and imaginary parts of sigma are related by the Kramers-Kronig relations, because obviously the response will be causal. So this is the kind of result that you obtain if you look at the real part of the conductivity, so what we usually call the conductivity. Here, if you don't have any lattice, you have a peak here, and this peak is just the resonance of the atoms at the frequency of the harmonic trapping, the global harmonic trapping in which they are confined. And now if you change the lattice beam intensity, you see that both the position and the global form of the peak change. So the shift is pretty trivial in the sense that when you crank up the intensity of the optical lattice, what happens is that there is a confinement associated with the lattice, and you increase this confinement, and you just increase this way the global trapping frequency of the atoms, the global harmonic trapping. So this shift is essentially trivial. What is not trivial is the overall structure of the peak. You see that when you increase the beam intensity, the peak broadens and its height decreases. And this is really a signature of a modification of interactions in the cloud, simply because when you increase the optical lattice, so as I said, you increase the global trapping, but you also increase the on-site trapping of the atoms. And when you do that, you modify both the tunneling, you increase the tunneling, and you also increase the on-site energy. And so you modify this way both T and U in the Hubbard model. And so these are the structure that we would like to understand. Why can we explain this this modification in the peaks? So the goal, so we want to describe and understand the relevant features of the resonance, relevant in the sense that are easy enough to describe and capture using simple models. And also, very importantly, usually we are interested more by homogeneous system. Harmonic traps are some kind of whim from the cold atom community because it's easier to realize a harmonic trap, but it's true that for real material, usually they look like homogeneous system. And so, is there a way to deconvolve the trap and the properties of homogeneous systems? Or another way to state the same thing, we know that there is something which is called the LDA, the local density approximation, that allows you to go from trapped system to homogeneous system using essentially the fundamental laws of thermodynamics for static properties. Is there an equivalent of the LDA for dynamical properties like the peaks that we observed? Obviously, this is not trivial because the peak, the main feature is the peak, and the peak is associated with the trapping potential, the harmonic trapping potential, which does not exist in a homogeneous system. And so, are there other features that we can extract from the experimental data that can relate to homogeneous materials? So essentially, when you see a peak like this, there are two features that you can try to interpret. First, the width of the peak, which, as we will see, as usual, is associated with some damping time, and that's going to be the transport time of the system. And the other feature, which is easy to address, is the surface, the area of the peak, or if you prefer, when you know the width, it's the height of the peak. We will be dealing more with the area of the peak, and we'll see that it's going to be related with some rules, can be interpreted using some rules. So I will start with the line width and what we can say about the transport time in the system. So the first thing, we would like to talk about transport. And if you think a bit, you see very quickly that having a dissipation in this kind of situation is not so obvious. The fact that you can have some decay, some dissipation, because if you start even for a very strongly correlated system, but in free space, so meaning that you have global momentum conservation and Galilean invariance of your system. If you try to measure the conductivity, essentially, it's a bit pointless because what's going to happen that you apply a force to all the atoms, and it's going to be the same force. And essentially what you're going to have is that the center of mass of your cloud will just accelerate as if it was only a single particle. And this just comes the fact that when you look at collisions between particles, two particles, the momentum P equal P1 plus P2 is conserved because you have a momentum conservation during the collision. And the velocity is just pi divided by m. So the total current associated with your two particles is also conserved. So the collisions do not modify the current. And so in the end, you will get something where interactions and collisions are simply irrelevant. Actually, when you add, so this is true for in free space, this argument will still work in a slightly modified way if you work in a harmonic trap. This is a so-called Con's theorem that tells you that even if you take a very strongly correlated system and you put it in a harmonic trap and you wiggle the center of mass of the trap, essentially what you're going to get for the center of mass motion of your cloud is the same as if you had just a single particle. So interactions will not play a role in the dissipation in a harmonic trap. Okay, so now we're going to say, okay, but we're not really in a harmonic trap, we have a lattice. And obviously in a lattice you should have transport, but if you look at a real material, usually the conductivity properties or the resistivity is due to the presence of defects in the system, either static defects, an atom which is the wrong one at the wrong position, or dynamical defects if you have phonons that changes slightly the distance, the relative distance between neighboring atoms. So in an optical lattice, you don't have any defects, dynamics or static. So it means that the origin of the dissipation is different, once again, from what you have in a real material. And actually, the origin of dissipation in our case is the breakdown of Galilean invariance. The fact that in a lattice, there's no longer this linear relation between the velocity and the momentum or the quasi-momentum. Because what we know is that in a lattice, what is conserved is the quasi-momentum of two particles, or the sum of the quasi-momentum of two particles, which is conserved up to a vector of the Brillouin zone of the reciprocal lattice, sorry. And if you look at the velocity, which is the derivative of the energy with the momentum, then this velocity is not proportional to p, but the sinus of p. And so if you look at the total current is not conserved during a collision. So there will be two effects that will damp the current of particles. This is what are called, first, simply the fact that we don't have a linear relation between V and P, and also these so-called umklapp processes, which tells you that quasi-momentum is not, strictly speaking, conserved. It's conserved up to a vector of the reciprocal lattice. So let's go to the experimental data. So the experiment is performed in a regime which is that I could call a classical regime, in a sense that, as we'll see later, particles can really be described within a Boltzmann equation regime, because the filling factor is very small, 0.1. So this is for practical reasons. You may know that in quantum gas microscope experiments, if you just take a direct picture of your atoms, what happens is that when you have two atoms in the same site, they actually annihilate themselves by photoassociation and cannot be counted. So working at very low filling factor allows you to have a good counting of your particles, and also high temperature in this regime. So the temperature is comparable with the tunneling. So this is really a weakly correlated regime. So it's, in the sense, this is a classical regime. In another sense, it's a really unusual regime, in the sense that usually in solid state systems, temperature is very low compared to the Fermi energy, filling factor is pretty large. And so this is actually a regime which is kind of unusual for solid state systems. Quite counterintuitively, high temperature regimes are unusual for solid state physics, because when you crank up temperature, your material melts, which is not the case of an optical lattice, because you're not coupled to the phonons. Anyway, so what matters to us is that you have a weakly correlated system. So you can do a very simple perturbation analysis. So essentially what happens is that when you have an atom in a state n prime, it's promoted to a state n by the external excitation. If you work out perturbation theory, first order perturbation theory, you get this very well-known formula for the conductivity. So n is the atom number, omega is the frequency, h bar is h bar. F of n and f of n prime are the populations of the states n and n prime. Omega and n prime are the Bohr frequencies between the two states. And you have these matrix elements of the dipole between states n and n prime. So what I call here states n and n prime are the states associated with particles trapped in an optical lattice plus a harmonic potential. So that may sound something which is not trivial, but actually Anna Maria Ray worked out the algebra to calculate this, the eigenstates. So they could actually find the spectrum of this Hamiltonian, where you have a non-interacting particle with just a kinetic energy and a trapping potential. So an optical lattice plus a harmonic confinement. So what you get in this case is two kind of, sorry, I went too fast, is two kind of states. Essentially, at point X, KXAL is the energy difference between two sites near X. So if you look at the energy difference between these two states or these two states, you see that when you go far away from the trap center, this energy difference will increase, and it increases linearly with X just because it's proportional to the slope of your potential. So when you are very close to the center, what happens is that T is much larger than KXL, so this energy difference. And so it means that by tunneling, the atoms can hop from one side to the next because the mismatch associated with the harmonic trapping does not prevent the tunneling. And so in this case, you have just tunnel delocalized states, which are your usual block states, which are characterized by an effective mass. And what happens is that you can describe everything as if you had this quasi-particle trapped in a harmonic trapping. And so the spectrum is just given by this formula where you recognize the spectrum of a harmonic trap, but with a renormalized frequency here, which is renormalized by the effective mass of your particles in a block state. So if you go there, what you have is that the tunneling is very small compared to the energy difference. And in this case, your states are localized because you cannot hop between two states. And so the separation is just given by the energy difference between these two states. So you just localized at the bottom of these wells here. And so the energy is quadratic like this and is given by the position of your sites. So it means that we can calculate everything in this case. And the thing that, if now we're interested by the imaginary part of sigma, and the real part, sorry, of sigma, which is given by the imaginary part of this thing here. And you know that you can expand this as a function of sigma, and what you get is a sum of Dirac term. So you have a series of Dirac peaks that correspond to these to the Bohr frequencies of the spectrum that I've shown you in the previous slide. So to get something which is more adequate to describe experiment, what we did is to add some phenomenological damping, just like what we have in atomic physics, where we know that the dipole is not just given by the tuning, but there's also some imaginary part here which is associated with damping. So what we did was to add a phenomenological damping to this formula. And what we did was to fit the experimental data using gamma as a free parameter. And so this is what you get when you look at the current dissipation rate gamma as a function of parameters, so the atom number, U square, because as you will see, interaction square is a measure of the scattering cross-section, and where lots of different parameters are varied, atom number, temperature, scattering length, and height of the potential. And so we'd like to understand this, this plot here. So what we did was to just work out some kinetic theory. And so using a Boltzmann's equation with a linearized correlational operator, which is just proportional to U square. So we expand the density matrix or the distribution close to the stationary distribution. And using a classical approach, this is what you get for the damping rate. And so you can work out these gamma. And so what is interesting here, so here's the damping rate as the function of the filling. So you have the experimental data, which are the points, and you can compare the role of umklapp and no umklapp, or clap, I don't know how we say, processes. So if you don't incorporate umklapp processes, you get something which is here, which is way too small. And you see that to account for, to redescribe the experiment, you need to account for umklapp scattering. Okay, now I would like to go to the second part, or the second feature that we'd like to describe is the area of the peak. So here we have some rule that tells us that when you integrate the real part of the conductivity, actually it's associated with the commutator between the position and the current operator. And so when you're in the free space model, this is just a constant. But now if you work in a lattice model, so you see that you have n divided by m, you get something which is kind of similar, except that the m, or the 1 over m, is replaced by the inverse of the effective mass tensor of your lattice. And this is really interesting because this is now a static property. And while this one is a dynamic property. And you remember at the beginning, I was mentioning LDA, and you can really apply LDA to calculate this thing here. You can assume you can slice your cloud in homogeneous part and calculate for a homogeneous system what is the effective mass of the average effective mass of your particles, and then add up all the slices to get access to this thing. And so you see that for a lattice model, actually, you can rely on LDA to calculate the area of your peak. And actually, what is also very nice is that this formula here is valid in the presence of trap and of scattering. So yes, just a little disclaimer that when you calculate this sum here in a trap, in a lattice, you don't want to integrate too far because you just want to stay in one band. If you integrate over the whole frequencies, actually what you get in the end is this result. So you have to restrict the frequencies over which you integrate to get this result in a lattice. So you can this way work out the expression here, and what you get is this simple expression here for the area, which involves the atom number again, the effective mass, and some modified Bessel function, and the tunneling and the temperature. So what is remarkable that it does not depend on interaction strength. This is because we're working in a weakly correlated system. It does not depend on the harmonic trapping. This is a consequence of the LDA. And it works whether you occupy this propagating state, delocalized states, or localized states. So this is a very simple formula that works also in a trap. So we can test the sum rule, the sum rule approach. So first test that there is no dependence on scattering. So you see that the area here in our regime does not depend on the interaction strength. It's because essentially at the static level, our system behaves as an ideal gas. And so these kinds of recover a quote from Mahan, who said that scattering does not destroy conductivity. It just redistributes conductivity over frequencies. And now if you look at the temperature dependence, so here you have again lots of experimental points with lots of parameters which have been varied, and you can compare with our formula, which is here, and you see that there is a very good agreement with between experiment and this simple model. So I'm done with here. I would have lots of other things to discuss, but there's not enough time, I guess. So just to recap, what we said is that we can measure something which is very reminiscent to conductivity, but in a trap. And so there are two things that we can extract, which is the scattering time, which is probably the less trivial quantity, and some rule which happens to be related, so the area of the peak, even though the peak itself is really strongly associated with the trap, its area can be recovered from a homogeneous theory using local density approximation. And this is a very nice feature of this experiment. So now the open question is, how can we go beyond the weakly correlated regime? And are there other dynamical features for which LDI applies? And for instance, I will just flash one slide about this to give you a flavor of what I have in mind, is that when you go in the high frequency regime, when you look at textbook electrodynamics of continuous media, what we say that sigma of omega, so the conductivity, that describes the properties of free unbound carriers, like free electrons in a metal. And when you consider a dielectric medium, so here the electrons are attached to molecules, and in this case, you prefer to describe the system as using a dielectric constant that describes the index, the optical index of the system. And the distinction between the two kind of carriers, the fact that in one case they are bound, and the other case they are unbound. Now, at high frequency, we know that because of their inertia, the motion of the free carriers is frozen. And so essentially, they don't move a lot, and their motion becomes localized. And in this case, at high frequency, you can either talk in terms of conductivity or dielectric constants. And so you see that at high frequency, the response of the systems become local. And so there must be a way to perform some local density approximation, but for the high frequency response of a strongly correlated system. And this is something that we would like to explore in the future. And on this, I think I'm done, and we'll be happy to answer your questions. Thank you.
Thank you. So questions, either click the raise hand button or type a question in the Q&A box. Luigi.
Thanks, Frederic. It's a very nice work and talk.
Thank you.
Yeah. So, question on the Drude weight.
Yes.
So it's the coefficient of the delta peak.
Okay, delta peak. This one, so probably you mean.
Yes. So typically, this Drude weight can be used to understand whether you have transitions in the system. For instance, metal insulator.
Yes.
Okay. So do you have any sign of this transition in your system? Because your system is with harmonic confinement. I mean, it's a little bit more complicated.
Yeah. So we can really extract. So so if you look at the peak, so we can really each part of the peak correspond to different region of. I told you about these localized and delocalized states. So the main peak here is associated with transition between delocalized states, because this is really these are really the transition in harmonic trap. So you go from one state to the other, and that gives you a well-defined resonance. And now, when you look at the wings of the distribution, they correspond to transitions between localized states, between the states of the Vannier ladder.
Yes,
and
but
of course you must add a broadening to on top of that.
Okay, but then I didn't get it, because are you talking about this is your experiment?
This is Joseph's experiment. But
okay. So you see a transition with the Drude weight.
So I'm not sure what you mean by transition. So we see that. So as I said, so if you excite atoms which are in this region here, their response will be in the main peak.
No. I mean, a transition means the following. So if you have a non-vanishing coefficient in front of the delta, Dirac delta in omega, then this is an ideal conductor.
Yes, so this is this matrix element here.
So then it's an insulator. This is the transition. It's a metal insulator transition. Is the Drude weight.
Yeah. Okay. So if you mean. Okay, if you mean a metal insulator transition, no, because the filling is very small, so there's no such thing. We are in a really classical regime where everything can be described using a Boltzmann law.
Yes. Okay. Clear. Thank you.
Anna.
Yeah. So hi, Fred. So also I like it very much. Your talk. Just a small comment. As you in your last question, you were asking other dynamical properties where LDA applies, and I have one answer. It works well for the dynamical structure factor. And once we tried that with Patrizia Vignolo, and we calculated both it in an exact way and with LDA, and it works really well.
Yes, so, okay. There was a slide that I couldn't show like this, but yeah.
Okay.
Yeah, I agree.
You can show it if you want.
Well, this is kind of related to the first thing I was saying with the first F-sum rule, which is kind of related to the same thing here. Because essentially, when you write, so maybe I can show my slide, which is here. So when you expand sigma of omega at large omega, you have this sum rule here, and as we said, this is related to the local properties of the system. And likewise, when you look at the second part, so the real part of the conductivity, that gives you dissipation, and dissipation will be something that's also local in this case. And so probably with the next term of the expansion, you can also use some local density approximation, and the
yes,
you can. Rule are here. The special factor is here.
Okay, perfect. Okay. Yes. Good.
So,
thanks.
Thank you.
So there's one question in the Q&A.
Yes, Roberta. Hello, Roberta. Since you put a lot of energy in the system, you start to have thermal effect. Does some rule still apply? Yes, the sum rule still apply in this case. As I was saying, it can take a different form depending on whether you stay in a single band model or not. Because if I show again the expression, so this one, yes. So when I say free space, actually, it's also valid if you have interactions between particles, if you have a harmonic trapping or not a harmonic trapping. So this is always true, actually, this sum rule. So the reason why we have this result is, as I was saying before, it's because we restrict all the dynamics to a single band model. Now you must make sure that you do not excite the single band, the next band, to be able to apply that. And the occupation of the second band was not very big, if I remember, in the experiments. Well, more to take care about next to nearest neighbor hopping than the interband hopping.